We want to use the first derivative test to determine any relative extrema of the given function. So the first step is to determine the possible locations of any relative extrema. And all relative extrema occur at critical numbers, which is where the derivative is equal to 0 or undefined. So the first step is to determine the derivative of the given function. Notice how our function is a quotient, so we'll apply the quotient rule to determine the derivative. So we'll let the function in the numerator equal f, and the function in the denominator equal g, and then we'll apply the quotient rule given here below. So we'll start with the denominator, which will just be the denominator squared of the original function. So we'll have x squared plus 1 to the second. The numerator is going to be g times f prime minus f times g prime, or the denominator times the derivative of the numerator, which is 5, minus the numerator times the derivative of the denominator, which would be 2x. Let's go ahead and simplify this numerator. So we'll have 5x squared plus 5 minus 10x squared. So our numerator simplifies to negative 5x squared plus 5 all over the quantity x plus 1 squared. Now the critical numbers occur where this derivative is equal to 0 or where it's undefined. Sometimes when we have a rational function, there are values of x that make the denominator equal to 0, which would give us a critical number. But since we have x squared plus 1, x squared is always positive, therefore the denominator is never going to equal 0. So now we need to determine where this quotient would be equal to 0. So we want to know when negative 5x squared plus 5 over the quantity x squared plus 1 squared is equal to 0. A fraction is only equal to 0 when the numerator is equal to 0. So we're really only concerned about when negative 5x squared plus 5 would equal 0. Another way to think of this would be to put this over 1, and then if we cross multiply, we'd have the same thing. When does negative 5x squared plus 5 times 1 equal 0 times the quantity x squared plus 1 squared, which is 0. Now this does factor. If we factor out negative 5, we'd have x squared minus 1 equals 0, and then we have a difference of squares. So the solutions are x equals negative 1 and x equals 1, which means our critical numbers are x equals plus or minus 1. Now we're going to use these values to divide up the domain of the given function and then test the sign of the derivative in each of those intervals. And since the domain of the given function is all real numbers, if we have the entire number line and then we plot our critical numbers of negative 1 and positive 1, you can see we'll have 3 intervals to test: on the left, in the middle, and on the right. So let's go ahead and organize this in a table. The leftmost interval is going to be from negative infinity to negative 1. The middle is from negative 1 to 1, and the interval on the right is from 1 to infinity. And now we'll pick a test value in each interval and then determine the sign of the derivative in each of these intervals. So let's use negative 2 for this interval, 0 for this interval, and positive 2 for this interval. And now we'll sub these values into the derivative function to see if it's positive or negative. And here's the first derivative from the previous slide. And notice how I did decide to use the factored form of the first derivative, but we could have left the numerator in expanded form if we wanted to. So now let's find f prime of negative 2, f prime of 0, and f prime of 2. So when x is negative 2, we're going to have negative 5 times, this will be negative 2 plus 1, that's negative 1. This is going to be negative 2 minus 3, that's negative 3. Our denominator is going to be negative 2 squared, that's 4, plus 1, that'd be 5 squared, or 25. And really all we need to know is if this is positive or negative. Since we have 3 negatives being multiplied together in the numerator, this will be less than 0 or negative. Now for f prime of 0, we'll have negative 5 times 1 times negative 1 all over positive 1. And this value is going to be positive, so over this entire interval, the derivative is positive. And then for f prime of 2, we'll have negative 5 times 3 times 1 all over 2 squared plus 1, that's 5 squared is 25. And we can see that the value of the function is going to be negative on this interval. So since the derivative is negative on this interval, the function is decreasing on this entire interval. Here the derivative is positive, so it's increasing. And then here it's negative, so it's decreasing. So let's sketch what this information represents. If the function is decreasing on this interval, that means it's going downhill on this interval. And then notice on this interval it's increasing, so it's going uphill on this interval. And then on the right it starts to decrease again. So that tells us that x equals -1, we have a low point or a relative minimum. And then at x equals +1, we have a high point or a relative maximum. Let's go ahead and record that. Again, we have a relative minimum at x equals -1, and we have a relative maximum at x equals +1. But notice how we still don't have the max and min values. To determine those, we have to sub these two x values back into the original function. Let's go ahead and do that. At f of 1, we have a maximum, so we'd have 5 times 1, that's 5, all over 1 squared plus 1, that's going to be 2. So the relative maximum is 5 halves at x equals 1, and then f of -1 will tell us the relative minimum. So the numerator would now be -5, but the denominator is still going to be +2. So the relative minimum is -5 halves at x equals -1. And sometimes you will see this information written as an ordered pair. So this would be the point 1, 5 halves, and this would be the point -1, -5 halves. But it is important to recognize that the y-coordinate or the function value is actually the max or min value, and the x-coordinate or x values represent the locations of the relative extrema. Let's go ahead and verify this graphically. Here's our relative minimum of -1, -5 halves, and here's our relative max, 1, 5 halves. Notice in red I did graph the derivative function. I did that just to show that notice how when the derivative function is equal to 0, we do have a relative min here, and where it's 0 here, we have a relative maximum. And that just reinforces the idea that relative extrema occur at critical numbers, which is where the derivative is equal to 0 or where it's undefined. I hope this example was helpful.